What's up guys, it's me, Sir Ernest, and today we're going to discuss freefall motion in the context of our lesson today, energy conservations or energy considerations. So this discussion will come from Fowles and Cassiday 7th edition, and this is related to example 2.3.1. Okay, so let's review first or set up our system. So let's say this is the ground, and the particle is said to start from the ground. So this will be your reference point. Now if the upward direction would be positive y, okay, we know that when projected upward with an initial velocity v naught, this will eventually go up, and it will meet a turning point. That is where the maximum position of, or the maximum height that this object will reach. Okay, so let's call that h. Okay, now and then after this turning point, this particle will eventually go down. Let's say somewhere here, the particle is now moving downward. Okay, so while the particle is moving up, it has an upward velocity. At the turning point or at the maximum height, v is equal to 0. So this is now your turning point. Okay, throughout the motion, there's only one force that acts on the particle. That is your gravitational field or the gravitational force, or your weight, where your weight is equal to negative mg j hat. Okay, so because throughout the flight, the only force acting on the system is a conservative force, which is gravity, we can define the potential energy associated with this force by this equation. So this is equal to negative derivative of u with respect to y, and the force is negative mg. So we can solve this differential equation. So this becomes integral of du, and this is equal to integral of mg minus integral of mg dy. Okay, so let's say at time arbitrarily the potential energy at the floor or at the ground is equal to 0. So the limits of integration becomes this, and then we can solve this. Solving this integration, we now have the potential energy will now be equal to mgy. As you will notice that the potential energy is a function of y. Okay, so this is now the potential energy. So therefore the total energy E, which is equal to the sum of kinetic and potential energy, will now be equal to 1/2 my dot squared, or v squared, okay, plus mgy. Okay, now imposing some initial conditions in our energy, wherein, for example, in using energy conservation, okay, where E is a constant, we can see that at the turning point, at the initial position, so that's E at the floor, will be equal to E anywhere, which is this one. So at the floor, y is equal to 0, so u is equal to 0. So the total energy at the initial point will just be your potential your kinetic energy at the floor, given by 1/2 m times their initial velocity v naught squared, or the v naught squared, or the square of the speed of your particle initially. From here, this is also equal to this one. So this is 1/2 m v squared plus mg1, which yields us, so again, you can cancel m, and then we multiply both sides of the equation with 2 or by 2, and then we'll end up with v squared equals v naught squared minus 2gy. So you will notice that what we obtained using energy consideration is the kinematic equation you used when you studied your free fall motion in your general physics class. Okay, similarly, the energy at the turning point, where y max is equal to h, okay, we can use this equation. So at y max equal to h, so this is your turning point, okay, the speed is equal to 0. So putting it here, this becomes 0 equals v naught squared minus 2gy. So in this case, y would be equal to h. So therefore, height is now dependent on the initial speed and the gravitational speed. So that means the more you put in kinetic energy on your particle, the higher the particle will go. Okay, so that's your that's example 2.3.1 of Fowles and Cassiday. So that's it. I hope you learned something today. Thank you guys for watching, and I'll see you guys in the next video. Bye bye.